Hello everyone, and thanks for watching my videos. In this video today, we're gonna be focusing on the pH of acid and base, and their behavior. So without further ado, here is the video, and I hope you enjoy it. Thank you.
How to determine the pH of a strong base. This is the same methodology as we did with the weak and strong acid. So there is nothing to change here. The only difference is what you are measuring when you are looking into the base. When you are looking into the base, you're measuring the hydroxyl ion concentration. If I put this in comparison with the acid, when you are measuring the pH of an acid, you are measuring directly the hydronium ion concentration. So the difference between the acid and the base is basically what are you measuring in solution. So how can you calculate the pH of strong base? It's the same methodology. It's going to be 100% dissociation, which means the 0.1 molar of the base is going to produce 0.1 molar of the hydroxyl ion and 0.1 molar of the B+, which is again the metal. This can be sodium, lithium, this can be any of these, metal ions. So these are strong base. Group 1A and group 2A will form strong base. So group 1A cations and group 2A cations will form strong base. Weak base are ammonia and its derivative. Any ammonia, any NH3, or any ammonia containing group, that will be a weak base. So right now we have, this is strong base, 100% dissociation, give you 0.1 molar. How use that model? Again, now we are calculating BOH. When you take minus log this, you are measuring the BOH right now, because this is the hydroxyl ion concentration. So this is the difference between the base and the acid. The base, you'll have to do one more step to get the pH. What is the one more step? Is to determine the pH from the equation that I told you. This slide is very important. Here is the equation that we're using for the base. The 14 equal pH plus BOH. So if you know the BOH, you can determine the pH by subtracting from 14. In this case, we are basically determining the BOH. The BOH is minus log 0.1, which is the hydroxyl ion concentration. Why we call it BOH one more time? Because we are taking minus log the hydroxyl ion. What we're measuring right now is the hydroxyl ion. So we're taking minus log the hydroxyl ion, which is 1. So this is not the BH, this is the BOH. And here is the equation that I highlighted. 14 equal BH plus BOH. This is 1. This is 14, that means the BH is 13. 2. If this was group 2, then it's going to be square, all 2, so this will be, so if this was group 2, then this will be again all 2, because you have 2 of them. So if I give this to be barium hydroxide, this will be barium, positive 2, and this will be 2 here. So again, this is very important idea. It's containing 2 hydroxide because this is group 2. This was group 1. Now this number here has to be multiplied times 2. Why has to be multiplied by 2? Because you have 2 hydroxide ion. So this is very, very important when you are dealing with group 2. This is the only difference between group 1 and group 2. If this was group 1, this is 0.1 molar. If this was group 2 cation, then this will give you 2 hydroxide ion. And if this is 0.1 molar, this has to be 0.1 times 2, because this is 2 moles of hydroxide ion. So this here will be 0.2. And this will be different, of course. And this will be. So one more time. If you are given any of these group 2 cations forming a base, and it's asking you to determine the pH. What is the pH of 0.1 molar barium hydroxide? The pH will be different than 0.1 molar sodium hydroxide. Why the pH is going to be different between these two, sodium hydroxide and barium hydroxide? Because there's a number of hydroxide ion in solution. This one has 2 hydroxide ion because you have 2 in the equation, barium hydroxide, all 2. So that will make this 2 times 0.1. So the concentration of the hydroxide is 0.2. And by getting minus log that, you will see that this value is, of course, different than the minus log 0.1. And once you get that, your pH again will be different. Sodium hydroxide, you don't need the 2 anymore because sodium is group 1. And you don't need the 2 here anymore. So this will be just 0.1. And we'll go back to our original equation, 0.1. So this is the difference. This is the contrast between group 1 cation and group, they're positive 2. That's why they need 2 hydroxide. This is how we write the structure for this, again, molecule. Calcium hydroxide, barium hydroxide, strontium hydroxide. So this is the contour of hydroxide. Again, so the last calculation is the pH of a weak base, which is follow the same calculations as the weak acid. We're going to run the ice table. We're going to follow again the product. But in this case, we are looking at the hydroxide ion concentration. For the weak acid, or the hydronium ion concentration. So in this case, we are looking for hydroxyl ion concentration. You're going to do the same thing. What you're getting is the BOH. So what you're getting from here is the BOH. So once you get the same thing, this X here for the acid was the hydronium ion. For the base is the hydroxyl ion. So to summarize the calculation for the pH of a base, you are determining the hydroxyl ion every single time. So when you're dealing with a base, you are getting the hydroxyl ion first, and then using, again, the BOH. So you're getting the BOH first. And once you get the BOH, you subtract it from 14, you will get the pH. This equation here is very important and is going to be used when you're calculating the pH of strong base or the pH of a weak base, BOH. When you take minus log X, you're taking minus log the hydroxyl ion. So once you get the BOH, what are you going to do? Subtract it from 14, you'll get the pH. So here's an example. Calculate the pH of 0.4 molar ammonia solution. Again, ammonia, this is a weak base, and any derivative of ammonia is going to be weak base. The Kb is 1.8 to -5. Here is the ammonia dissociation. Here is the reactant. Here is the product. Here is the initial concentration of ammonia, 0 at the beginning. We lost X from the reactant. We gain X in the product. The equilibrium is 0.4 minus X. The equilibrium is X and X. We set up the equilibrium constant. Kb is the base dissociation constant. So K here, the equilibrium constant has been covered in every single topic since we covered chapter 15. It just has different names. When you say Kw, that's the equilibrium constant for the dissociation of water. When you say Ka, this is the equilibrium constant for the dissociation of acid. When you say Kb, this is the equilibrium constant for the dissociation of the base. Every single time you have an equilibrium, this is an indication of the equilibrium process. Any reaction that has these 2 half arrows like this, that means this reaction is undergoing through an equilibrium process, which means all the equilibrium fundamentals will apply for that reaction. All right, so right now we have Kb equal product divided by reactant. Why water is not there? Because again, remember, water is pure liquid. Any fundamental that we cover in chapter 15 will apply to these, again, substance. So What is the KB? Here is the KB, which is given to you. What is X? That's unknown. 0.4 minus X. We ignore X. And again, we end up with X squared divided by 0.4. So what is X again? X is the hydroxyl ion. From the dissociation, you can tell that X is the hydroxyl ion concentration. While for the acid, your X is the hydronium ion. All right, so from here, the BH will be minus log the hydronium ion. How you get? So if you determine the hydronium ion from the hydroxyl ion, and then take minus log the hydronium ion, that will be again the BH, that will be 11.43. So this is again all the calculation in this chapter. And as I said, it depends on what substance you're dealing with. Strong acid, weak acid, strong base, weak base. Here are the KB values for the different base. This is all of them you can see contain nitrogen. Again, nitrogen containing substance is a weak base. And here is the KB, and here is the conjugate acid. Remember, if this is the base, this will be the conjugate acid by giving H+. So you can get the conjugate acid by adding H+ to all of them. And here is the conjugate acid. So how can you calculate the Ka? If this is the acid right now, how you can calculate the Ka? Well, Kb times Ka equal 1 times 10 negative 14 by using Kw. Ka is the acid dissociation constant, Kb is the base dissociation constant, and Kw is the ionic product of water. So clearly you can find the other by basically dividing by Kb or Ka. So if you're calculating Kb, divide by Kw by Ka. If you're calculating Ka, you divide Kw by Kb. And the same relationship apply. The BKA plus BKB equal BKW, which equal 14. So this is the same relationship as the Ka will give you the hydronium ion concentration. The Kb will give you the hydroxyl ion concentration. This is how Ka and Kb relate to the acid strengths and the base strengths. If Ka is very high, you have a lot of hydronium ion in solution. If Kb is very low, you have low concentration of hydroxide ion in solution. So this balance here, if they equal each other, then this is neutral. When Ka equal Kb, they have to equal 10 negative 7. Why? Because Kw is 10 negative 14. So if these two equal each other, it has to be 10 negative